about flash memory. As you can see in this page, there is a structure of the flash memory. What is different from other devices? There is a floating gate between the control gate and the substrate. Floating, as you can guess from the floating gate, the floating gate is like a floating stage. It means there is no bias and no connection with other devices. And floating gate is metallic or heavily doped uh, heavily doped. And for flash memory, we use FN tunneling, which abbreviation is Fowler-Nordheim tunneling. For the light operation, there is two types of lighting operation. First one is by grounding the source and drain. There will be electron supplies, and there will be a lot of electrons in the channel, and the electrons will gonna tunnel through the oxide, and it will be saved in floating gate. And for the hot carrier injection, we do not ground the both of the source and drain. We ground for the drain, and we give bias on the source. So if the ground supplies the electrons in the boundary of the source and the floating gate, there will be a hot carrier injection. So the electrons will gonna inject through the oxide to the floating gate. And if you wanna erase, use like this mechanism, we give reverse bias if we want erase. And for the hot carrier injection, we use avalanche effect. And for the flash memory, it has very big advantage compared to other SRAM or DRAM. DRAM. It does not need refreshing operation, and it is non-volatile device. So if we up the power, the data will gonna be retained. And this is the flash memory, and this is the threshold and ID graph. For SLC, it is single level cell. It is 1 bit, and multi-level cell, which we also call as MLC, it is 2 bit, and it has three threshold voltage for MLC, and for triple level cell, which we also call as TLC, it has 4 bit devices. And for state 1, there is no charge, so no carriers are moving. And if we lightly charge, there will be some of the tunneling effect. So the electrons will gonna tunnel through the insulator and get to the floating gate. And if we give the medium charge, the more will be on the floating gate, and if we give the highly charged, the more electrons will gonna be saved in the floating gate. And this is for SLC, we use 2 bit, and this is for MLC for 1 bit, 2 bit, and 3 bit. And there for SLC we use only single threshold voltage, but for MLC there is a 3 threshold voltage to classify the the memory, and there is 7 threshold voltage for TLC. But we have to make enough margin between the date to date. Yes, and there is a TLC NAND problem. If the level cell is getting numerous, the device's reliability will gonna decrease, and the margin will gonna decrease as well. So the oxide breakdown could occur. So by this operation, threshold voltage will gonna change. And this is floating gate structure. The floating gate structure is very old technique. The left side is the old one, which is we also call split gate. But it was really hard to realize or engineer. So we compensate this structure to the right side of the tunneling window structure. The reason why the drain side of the oxide is very thin is because we use tunneling through the drain and floating gate surface. The oxide should be very thin to give tunneling current, tunneling operation. And here is word line, but in this picture, word line is poly to PGM. PGM is abbreviation of the programmable gate meter. It is same as word line. And for device architecture, left side is the NOR architecture and right side is the NAND structure. And for the NOR architecture, it is very easy to assess, but each side is very big compared to NAND. So each space will gonna very big. For NAND architecture, it is simple and it is smaller than the NOR because it has lower wiring than NOR architecture. It is simple and cheap, but each operation will gonna very longer than the NOR architecture because RC time constants. So nowadays we usually use NAND architecture for the economical issue. And there is a difference between NAND and NOR. NOR is random access by cell and it has high speed and large area. But for NAND structure, it is random access by block and it is slow speed and small area. But even though they have such disadvantage, we use NAND because it is we can use more. It is very small. And for gate stack, there is 3 types of gate stack. First is floating gate, and second is Sonos, and third is Thanos. What you have to focus on this section is floating gate because Sonos and Thanos is not realized yet. And to introduce briefly, Sonos is a charge trap flash. We use nitride. We insert nitride on the oxide, but as you can guess in this engineering, it is very hard to realize. Also in Thanos we use titanium, but it is also very hard to realize. And nowadays we are focusing on VNAND because it is very revolutionary in the engineering. And as I told before, NAND is very good for the controllability, and we stack the float gate in the vertical structure. And yes, it improves the controllability by the stacking in the vertical side. And the white line is polysilicon, and this part is source, and this part is drain. And for RLAM is an abbreviation of the resistance random access memory, a type of non-volatile random access memory that works by changing the resistance across a dielectric solid-state material, often referred to as a memristor. And each advantage is each structure is very simple, but each device has issue about reliability. And it is some kind of capacitor, and capacitor has a lot of resistance, so almost no current flows through them. But if we increase the bias, at one moment the filament will gonna be created, and the current will gonna be rise abruptly, and we use this mechanism. And this is type of RLAM. If we going to the left side, it's field dominating, and thermal if we go to the right side, it's thermal dominating structure. As I told before, we now developing VNAND, but as like a VNAND, we are planning to make RLAM as a vertical structure for the controllability. Yes, and thank you for listening.